Imagine you're holding your favorite coffee mug. It slips from your grip, tumbles through the air, and explodes into fragments across your kitchen floor. Ceramic shards spread everywhere, some pieces big, some microscopic, the sound of impact still echoing in your mind. Now here's what I want you to do. Just stand there. Don't move. Don't clean up. Just wait. Wait for those scattered pieces to spontaneously lift off the ground, spiral upward through the air, and snap back together perfectly in your palm. A fully intact mug, as if nothing ever happened. You could stand there for hours, days, years. It's never going to happen. We all know this instinctively. But have you ever stopped to ask yourself why? What is it about the universe that makes this scenario impossible? The truth is, reality operates with a directional bias that seems absolutely fundamental to our existence. Things fall apart. They don't spontaneously reassemble. Ocean waves crash against coastlines and dissolve into foam and spray. You'll never see that foam suddenly organize itself, rise up from the wet sand, and launch backward into the ocean as a perfectly formed wave. This seems obvious, almost too obvious to question. Yet this apparent triviality hides one of the deepest mysteries in all of physics. The difference between past and future isn't written into the fundamental laws of nature the way you might expect. And understanding why reveals something profound about time itself and the universe we inhabit. Scientists sometimes demonstrate this principle by showing footage of everyday events played in reverse. A diver leaping gracefully into a pool becomes, when reversed, a person explosively ejecting from water and landing perfectly on a diving board. An egg splattering on pavement becomes an egg assembling itself from liquid and shell fragments. When audiences see these reversed sequences, they laugh. The laughter is instinctive. These reversed events violate something we understand at a gut level about how reality works. But what exactly are they violating? If you think about it carefully, the asymmetry between past and future permeates everything about conscious experience, not just physical events. We remember what happened yesterday. We don't remember what will happen tomorrow. That distinction seems trivial until you realize how strange it actually is. Our entire psychology revolves around this temporal asymmetry. We feel we can influence future events through our choices and actions. Nobody believes they can change what already happened. Regret, guilt, nostalgia, these are emotions that exist only because the past feels fixed, while the future feels open. Hope, anxiety, anticipation, these exist because the future feels uncertain. If you accept that humans are made of atoms, and atoms obey physical laws, then you'd naturally expect this obvious directionality to be built into those physical laws at the most fundamental level. It would make perfect sense if the equations governing atomic behavior simply didn't work in reverse. If there was some basic principle preventing particles from running backward through their trajectories. The universe would be designed such that everything naturally flows from organized states toward chaotic states. And the laws themselves would enforce this one-way flow. Except that's not what we find, not even close. When physicists examine the actual laws governing matter and energy at the deepest levels we've been able to probe, they discover something shocking. Those laws don't distinguish between past and future at all. They work equally well in both temporal directions. If you could film a single atomic interaction and play it backward, a physicist studying that reversed footage couldn't tell you which direction was forward in time. The mathematics works identically either way. Let me give you a concrete example using gravity, one of nature's most familiar forces. Imagine a planet orbiting a star. It traces an elliptical path through space, speeding up as it approaches the star, slowing down as it moves away. The area swept out by an imaginary line connecting planet to star remains constant over equal time intervals. That's Kepler's law. Now imagine filming this orbital motion and playing the footage in reverse. What do you see? You see a planet orbiting a star in an ellipse, speeding up and slowing down in perfect accordance with the laws of gravity, sweeping out equal areas in equal times. The reversed motion is just as valid as the forward motion. There's no way to determine which version is real and which is reversed. Gravitational physics is completely time-symmetric. The same principle applies to electromagnetism. If you reverse the flow of time in Maxwell's equations, they remain valid. The same for the strong nuclear force that holds atomic nuclei together. The same for the weak nuclear force responsible for certain types of radioactive decay, though there are subtle complications here that physicists only discovered relatively recently. But the key point stands. The fundamental laws governing matter at the smallest scales don't have a built-in arrow of time. They permit the universe to run forward or backward with equal validity. So how do we reconcile this with the obvious one-way nature of everything we actually observe? If the underlying laws don't enforce directionality, where does the irreversibility of everyday phenomena come from? Here's where we need to look more carefully at what's actually happening in irreversible processes. Consider planetary motion again, but more realistically. Earth's rotation is gradually slowing down. This happens because of tidal friction. The gravitational interaction between Earth and the Moon creates bulges in Earth's oceans. And as Earth rotates under these bulges, energy dissipates as heat. Friction clearly seems irreversible. If you push a heavy block across a rough floor, it slides and stops. The kinetic energy transforms into heat, into random molecular motion. You can wait forever, and that block will never spontaneously cool down while accelerating back toward your hand. Friction appears to be a genuinely one-way process. But when you examine friction at the molecular level, something interesting emerges. The organized motion of the block transforms into disorganized, random jiggling of countless atoms in both the block and the floor. The energy hasn't disappeared. It's just been redistributed into thermal motion. And each individual atomic collision during this process is perfectly reversible according to physical law. The irreversibility emerges from the sheer number of particles involved and the transition from organized motion to disorganized motion. This gives us the essential clue. Let me illustrate with a different example that makes the principle crystal clear. Imagine you have a container divided by a partition. On one side you have water mixed with blue dye. On the other side, pure clear water. You carefully remove the partition and wait. What happens? The blue dye gradually diffuses through the clear water. After sufficient time, you have uniformly light blue water throughout the entire container. The mixture has become homogeneous. Now continue waiting. Keep watching this uniform blue water. Will it ever spontaneously separate itself back into deep blue on one side and clear on the other? Obviously not. You could wait billions of years and it wouldn't happen. Yet here's the fascinating part. If you could somehow reverse the velocity of every single molecule in that container at an arbitrary moment, the mixture would unmix. The dye molecules would migrate back to one side, the clear water molecules to the other, until you had the original separated state. This isn't a violation of physical law. It's permitted by the microscopic dynamics. It just never happens spontaneously. To understand why, imagine zooming in to watch individual molecular collisions. Film these collisions at the molecular level. You'd see one molecule approaching another. They'd collide, and they'd bounce off in new directions. Now play that footage backward. You see two molecules approaching from different directions, colliding and bouncing off. A physicist analyzing this reversed collision would find it completely consistent with the laws of molecular dynamics. Every individual interaction is reversible. But now pull back and look at the big picture. Start with separated blue and clear water. The random thermal motion of molecules causes them to gradually intermix. That makes sense. Random motion from a segregated starting point naturally produces mixing. But imagine the reverse. Start with uniformly mixed water. Through completely random molecular collisions, the blue molecules somehow coordinate their movements to all end up on one side, while clear water molecules all migrate to the other side. That's not forbidden by physics. It's just stupendously unlikely. Absurdly unlikely. The number of possible molecular arrangements corresponding to mixed vastly outnumbers the arrangements corresponding to separated. When molecules move randomly, they overwhelmingly tend toward the more numerous mixed states. That's the entire secret of irreversibility. Things don't happen in reverse, not because the laws forbid it, but because the statistics make it virtually impossible. It's not illegal for a broken cup to reassemble. It's just that there are countless trillions of ways for the pieces to be scattered, and essentially one way for them to form an intact cup. Random molecular motion starting from a broken state will never accidentally produce the coordinated movements necessary to reassemble the cup. The probability is so infinitesimally small that it effectively never happens in our universe. If you confine just a handful of molecules in a small box, you could actually observe them spontaneously segregating occasionally, purely by chance. With only a few particles, the improbable becomes observable. But real objects contain not thousands of molecules, not millions, but approximately 10 to the 23rd power molecules, a number so large it's hard to comprehend. With that many particles, the probability of spontaneous organization from disorder becomes effectively zero. The universe hasn't existed long enough for it to happen even once. This reveals something crucial about the nature of time's arrow. The apparent irreversibility of natural phenomena doesn't arise from irreversibility in fundamental physical laws. It emerges from statistics combined with a critical boundary condition. The universe started in a highly organized low entropy state. Everything we observe follows from that initial condition, combined with the random interactions permitted by reversible physical laws. And this leads to a fascinating capability. If you encounter a partially mixed system, blue dye, that's mostly but not entirely diffused through water, you can make inferences about its history. If someone shows you a glass where one end is deep blue, the middle is light blue, and the far end is nearly clear, and they tell you this glass has been sitting undisturbed for 30 minutes, you can confidently conclude it was more segregated in the past. The blue was more concentrated, the clear water clearer. If you wait longer, it will become more uniformly mixed. This ability to infer past states from present conditions is the foundation of entire scientific disciplines. Physicists typically predict forward in time. They say, given these initial conditions, here's what will happen next. But historians, geologists, paleontologists, and archaeologists do something different. They predict backward. A paleontologist finds a particular type of fossil in one location and predicts that if you dig in similar geological strata elsewhere, you'll find similar fossils. A historian examining documents about Napoleon predicts that other documents yet to be discovered will corroborate the same basic facts. These predictions about past events are actually predictions about future observations. They work only because the past was more organized than the present. The fossils exist in organized strata rather than randomly scattered. The documents contain correlated information rather than random text. How did this organization come about? Some physicists once proposed that the universe simply exists in eternal random fluctuation. Occasionally, by pure chance, a region fluctuates into a more organized state. We happen to exist during such a fluctuation and are now watching it dissipate back to randomness. This theory has a fatal flaw. If our current state resulted from random fluctuation, the most probable version of that fluctuation would be the minimum necessary to produce our observations. There would be no reason for anything beyond our immediate vicinity to be organized. If you encountered an unexpectedly organized small region in an otherwise random universe, you'd predict that regions you haven't examined yet would be disorganized. But when we look at distant stars we've never observed before, we find them organized into the same patterns as nearby stars. Every time we examine a new region of space, we find structure, not chaos. Every new fossil discovery fits into an organized evolutionary history. Every new historical document corroborates existing narratives. This consistent discovery of organization wherever we look tells us the universe didn't arise from fluctuation. It tells us the past really was more organized than the present across the entire observable universe. Therefore, we must add to the fundamental laws of physics an additional postulate. The early universe existed in a state of extraordinarily low entropy, high organization. This statement is itself time asymmetric. It says something about the past that doesn't apply to the future. It falls outside what we traditionally call physical law, because we're accustomed to distinguishing between laws that describe how systems evolve and boundary conditions that describe how systems begin. Perhaps someday we'll have a deeper theory that explains why the universe started organized. For now, we simply observe that it did, and this observation is essential for making sense of irreversibility. Let me illustrate the mechanics of irreversibility with a specific machine. Imagine a ratchet mechanism, a wheel with sawtooth-shaped teeth, and a spring-loaded pawl that catches the teeth. This device can rotate freely in one direction. When you try to turn it backward, the pawl jams against the teeth and prevents motion. When you turn it forward, the pawl clicks over each tooth. It seems fundamentally irreversible. Now imagine attaching vanes to this ratchet wheel and placing the assembly in a gas-filled chamber. Gas molecules constantly bombard the vanes from random thermal motion. When they push the wheel backward, the ratchet jams. When they push forward, it clicks around. You might think you've created a device that extracts useful work from random molecular motion, perpetually turning in one direction. But examine what happens in detail. When the wheel advances, the pawl lifts and snaps down against the next tooth. It bounces. During that bounce, the wheel could slip backward. To prevent this, you need friction to stop the bounce, and friction generates heat. As the pawl heats up from repeated impacts, it begins jiggling from its own internal thermal motion. Eventually, it bounces up high enough and frequently enough that teeth can slip past it in either direction. The outcome depends on temperature difference. If the vane side is hotter than the pawl side, the wheel turns one direction. If the pawl side is hotter, it turns the opposite direction. Once both sides reach the same temperature, thermal equilibrium, the wheel doesn't turn at all. This demonstrates a profound principle. Phenomena run in a preferred direction only when systems are out of equilibrium, when one part is more organized or hotter than another. The conservation of energy tells us that total energy never changes. The ocean contains enormous thermal energy in the random motion of water molecules. But that energy is practically useless to us. To extract useful work, we need a temperature difference. Energy itself is conserved. The availability of energy constantly decreases. This is entropy. Entropy measures the unavailability of energy for doing work. The second law of thermodynamics states that entropy always increases in isolated systems. Things at different temperatures, left alone, equalize. Things at the same temperature don't spontaneously separate into hot and cold regions. Available energy always decreases. This is the arrow of time. Here we have a situation where an obvious macroscopic phenomenon, time's arrow, irreversibility, the distinction between past and future, is not an obvious consequence of fundamental laws. The connection is indirect, subtle, requiring extensive analysis to understand. Yet this phenomenon is absolutely central to existence. Memory, causation, identity, the difference between past and future, all depend on entropy increase. Understanding this requires more than just knowing the laws. It requires understanding how complexity emerges from those laws. Like a glacier. When you watch a glacier flow, you see ice moving, rocks tumbling, crevasses forming. You don't need to know that ice forms hexagonal crystals at the molecular level. Yet the properties of those hexagonal crystals, if understood deeply enough, explain why glaciers flow the way they do. The connection takes enormous intellectual work to establish. In fact, we still don't fully understand glacier mechanics from first principles, despite knowing the molecular structure of ice. This is characteristic of nature. The most important phenomena in the real world are complicated, emergent results of many fundamental laws working together in systems with countless interacting components. So let me synthesize everything we've covered. Why can't time run backward? Why don't shattered cups reassemble themselves? Why doesn't spilled milk uncollect itself into the carton? Not because physical laws forbid these events. Every molecular collision, every electromagnetic interaction, every quantum process works identically forward and backward in time. The reason is probability. Statistics. There are vastly more ways for a system to be disordered than to be ordered. A cup has one configuration where it's whole and functional. It has quintillions of configurations where it's broken. When the cup breaks, it transitions from one specific ordered configuration into one of quintillions of possible disordered configurations. That transition is probable. But the reverse, quintillions of atoms accidentally coordinating their motion precisely enough to reassemble into the one ordered configuration, is so improbable it never happens. Not across the entire history of the universe. The deep truth underlying everything, the universe began in an extraordinarily organized state. The early universe had incredibly low entropy. Ever since that initial moment, it's been evolving toward higher entropy states, becoming more disordered, more mixed, more uniform. Entropy increases relentlessly, everywhere, always. That's what creates the arrow of time. That's why you remember yesterday but not tomorrow. Why causes come before effects. Why you age rather than grow younger. Why structures decay instead of spontaneously forming. The universe is running down from an initial organized state toward eventual heat death. And remarkably, nothing in the fundamental laws requires this. The laws themselves work perfectly well forward or backward. Time reversal symmetry is a feature of the microscopic laws. But the universe started organized. That initial low entropy boundary condition, combined with the statistics of large numbers, creates the illusion of time flowing in one direction. We still don't know why the universe started organized. We don't have a deeper theory explaining that initial condition. It remains one of the great unsolved mysteries in physics. But we observe that it did start organized. And from that single fact, combined with reversible microscopic laws and probability, emerges everything we experience about time's passage. The past hasn't really gone away in the sense that its influence persists absolutely in the present state of the universe. Every current configuration encodes information about past configurations through the gradient, from higher to lower entropy. That's the answer. And once you understand it, it fundamentally changes how you perceive reality, causation, and time itself.